In this video, I'm going to talk about what acoustic scale observations mean for the interpretation of dark energy, in particular using cosmic microwave background to measure the peak in the spectrum, and using BAO, particularly from the recent DESI DR1 and DR2 data. It's based on this paper with my student Ewan Chamberlain, which has now been fully updated for the latest DESI DR2 results. So what we see is this recombination surface here. So I've shown us with us on the left today, looking out on the sky at this sound horizon scale at recombination. So this co-moving size here is the thing that we're hoping to be able to predict or measure. But what we can't do is measure it directly because, of course, we don't live at recombination. The thing we can actually measure is the angular size on the sky, theta star, of this acoustic horizon scale. And if we know what RS is and we measure theta star, that allows us to infer the co-moving angular diameter distance to recombination. So this angle is measured incredibly accurately now because there are a very large number of hot and cold spots on the sky measured by the Planck satellite and other CMB observations like ACT and SPT. There's now an extremely accurate measurement of the characteristic size of the perturbations in angle on the sky, given by this theta star. This is about 0.03% precision now, so it's almost as accurately as we know the temperature of the microwave background. So in terms of the power spectrum, this acoustic scale RS corresponds to the position of the peak in the CMB power spectrum, which is extremely well measured. That gives us this theta star. So we can basically think of this now as basically a known constant. It's measured much better than almost anything else apart from the temperature. So people don't normally talk about varying the temperature of the microwave background because it's so well measured. So really, for most models, you don't have to worry about varying theta star either, because it's so much better measured than anything else. It's basically a known constant. We've also got this very nice measurement of the shape of the spectrum, the microwave background here, with these peaks and troughs, and they tell us a lot about the matter contributions in the early universe, as well as the photons and the neutrinos. And from that, we can infer the baryon density and the matter density, not quite as accurately as the acoustic scale theta star, but still at the percent level. So these are very well measured now. Okay, so that was the acoustic scale measured by the CMB. What about the baryon acoustic oscillations, the BAO? So here you're basically measuring exactly the same scale as the acoustic scale, except that now it's the scale at which the baryons separate from the photons, which is very slightly different, but basically they're the same number and they're just proportional to each other with a slightly different numerical factor. It's about 147 megaparsecs for the co-moving sound horizons for when the baryons decouple from the photons, which determines the BAO scale, compared to where the photons decouple from the baryons, which determines the microwave background scale. But it's basically the same scale. So we see this same physical scale at recombination in the CMB acoustic scale, and we also see it transverse to the line of sight at a given redshift in the baryon acoustic oscillation scale. So what we're measuring is this angle theta BAO, which gives you a ratio of the co-moving sound horizon to the angular diameter distance to that redshift. So again, it's the angle is the thing you can actually measure. But if we know RD, because it's inherited from the early universe, which we understand, then that allows you to infer the angular diameter distance. You can also measure the interval of redshift between this scale along the line of sight, and that translates into a measurement of the expansion rate at a given redshift multiplied by this same sound horizon scale. So these are the observables. So there's a line of sight BAO distance DH, which is sometimes written C over H. I'm going to use natural units here from now on. And there's a transverse angular diameter distance, which you get from the angular size of the acoustic oscillations, assuming you know what the sound horizon is. People sometimes parameterize it instead in terms of the angle averaged BAO scale DV. So that's basically some sort of average of the transverse and the line of sight scales. And the Alcott-Puczynski parameter FAP, which is the ratio of the two distance scales, DM over DH. So you can either parameterize things in terms of DH and DM or DV and FAP. It's just different ways of representing the same information. So what can we learn about dark energy from the BAO measurements that we've got? How can we vary the dark energy model in a consistent way to fit the data that we have? So I'm going to assume here that the physical densities are fixed, the matter density, the baryon density. So we know from that the drag scale, the sound horizon scale, And we also know the evolution of matter, because we've measured how much matter there was in the early universe, and we're assuming it's non-interacting. So from that, we can just infer the matter density at any given time. Theta star is very well measured, it's basically fixed, so that tells us the angular diameter distance to last scattering. dm z star is fixed. Then we're also going to talk about null energy conditions. So this is a sort of key, not necessarily true, but probably true in most sensible models. You satisfy the null energy condition, which in the context of cosmology is basically saying that as the universe expands, the density of the dark energy can't increase. Remember, a cosmological constant, the density is constant as you expand the universe. If you violated the null energy condition, the density would actually increase as you made the volume bigger, which would be extremely weird. So normally in theories, they become unstable or something if you have null energy condition violations. Okay, so now we're going to use the null energy condition and the fact that the angular diameter distance has to be fixed. And we're going to be comparing the ΛCDM model to some other dark energy model. We're not going to make any assumptions at all about what the other dark energy model is, other than that it's non-interacting and that it satisfies the null energy condition. But we know the angle of theta star on the sky, and that means dm z star has to be the same whatever the model is. And if you write down these two integrals that determine dm, so dm is just the integral of dh between us and last scattering, and that has to be the same empirically whatever the dark energy model is. So we've got these equalities here relating these two integrals. But we know that the dark energy density can only increase with redshift, assuming the null energy condition. So the only way these two integrals can be the same if the dark energy density is increasing with redshift, if the value today of the dark energy is actually less than it was in ΛCDM. So that tells you the dark energy density today is less than rho lambda. And if you translate that via the Friedmann equation into a constraint on H, that tells you the Hubble parameter today in a dark energy model that satisfies the null energy condition has to be lower than the value we infer in ΛCDM. So one consequence of this is if you want to put in dark energy, you're only ever going to lower the inferred value of H0 unless you violate the null energy condition. So adding dark energy generally doesn't help in these simple cases with the tension in the Hubble parameter. It only lowers H0, it can't increase it. So what does the evolution look like typically? So you've got this constraint that the integral of dh has to be fixed. Whatever the model is, you have to get the same angular size of the sound horizon in the microwave background. So that means if you take the ΛCDM and look at the difference in some other model, you'll find that there has to be an equal area above this curve as below this curve when I plotted the evolution in redshift. So there has to be some critical redshift ZC at which the values of dh are equal to the value in ΛCDM. High redshift, I'm assuming that there's no dark energy, so everything converges. So the two dHs, the Hubble parameters, are both the same at very high redshift. So this ratio converges to 1, so the difference goes to 0 at high redshifts. So you start above it. dH starts above the value of lambda in ΛCDM. You cross over at some critical redshift, and then it stays below and gradually asymptotes back towards being the same at very high redshifts. So for Z less than this critical density here, we've got dH bigger than the value in ΛCDM. And that means that if we calculate the angular diameter distance, which is the integral of dH, that just has to be bigger than the integral in ΛCDM, and therefore it has to be bigger than the angular diameter distance in ΛCDM. If Z is bigger than ZC, then you can work out how the difference between the angular diameter distance in the dark energy model and ΛCDM evolves with redshift. So the derivative of dm is just dH, and we know that at bigger than ZC, dH is less than the value in ΛCDM, and that means that this term here is negative. So what that actually means is that because it's monotonic, dm is above the value in ΛCDM here, and it's going to asymptote to being equal here, and here, because it's monotonic, that tells you that it has to be bigger than the value in ΛCDM for all Z. So actually the null energy condition gives you a very stringent constraint on the values of the angular diameter distance you can have at any redshift. It always has to be bigger than the value in ΛCDM. And you can keep playing this kind of game and infer various inequalities for all the other observables. So what about the DESI data? So these are the DESI data as shown by the DESI team. So here they plotted these various different ratios against the ΛCDM. So 1 here is the lambda CDM model, except that here the lambda CDM model is the best fit to DESI alone. So if you plot the Planck best fit lambda CDM model, then you get these dashed lines here. And you can see that by eye, it looks as though there's a little bit of tension here with some of these points being off. But remember that some of these points are quite correlated. So it's actually, I think, easier to look at it in the two-dimensional space. So this is what I've done. I just added the DESI points. The evolution line here shows the evolution of a best fit Planck early lambda CDM plus DESI fit, allowing for W0, WA, CPL parameterization. So the points here, there are quite large error bars. The points in DH and DM are quite a lot more correlated than they are in FAP and DV. But you can see that there are, again, some slightly outlying points here. So LRG2 is down here. But the direction in which this point is pulling things is precisely in the direction that is not allowed by the null energy condition. So it's firmly inside these exclusion regions. What does this look like in the W0 WA plane? So here I'm talking about at fixed theta star and rho m. So this is the relevant for combining with the CMB acoustic scale and early universe constraint on the matter density. So the point on the left here at omega naught is 0 and WA is 0. That is, of course, lambda CDM. So there the Hubble parameter would be the standard Hubble parameter in lambda CDM. And then you've basically got if you go away from that point, there's exactly one line where the Hubble parameter remains exactly the same. And that's this black line that's shown here, which is approximately where WA is -4 times 1 plus W0, deviating a little bit at higher redshifts. Below that line, the Hubble parameter is actually becoming larger than it would be in lambda CDM, and that violates the null energy condition. So this whole bottom part of this plane here violates the null energy condition at all redshifts. The coloured lines show where the angular diameter distance at a given redshift is equal to the value in lambda CDM. So this green line here, for example, is where at redshift 0.5, the angular diameter distance is exactly the same as it would be in lambda CDM. So for any point in the plane below this line, the prediction for DM would violate the constraints that we've derived. So if you're in this region down here, then the sign of the prediction in this model, in the W0 WA model, violates the null energy constraint. It's exactly equal at here, and up here then it's okay. So as you go to higher redshifts, you gradually move towards the top here. So the bottom line is where you are inconsistent with the null energy condition at all redshifts. And you go up to these higher lines, you become consistent at some redshifts, and eventually at the top here, you become consistent with the null energy condition at all redshifts. But the message from this is that if you have contours that lie on this plane, say below this green line, then the predictions of all the models below that green line at redshift 0.5 have predictions for DM, the angular diameter distance, that are inconsistent with the null energy condition. So there's no consistent interpretation of DESI data at redshift of 0.5 that satisfy the null energy condition and giving you contours below that line. So on the left here, I've shown the contours basically the same as derived by the DESI team for Planck early lambda CDM plus the DESI data. And here I've shown the redshift 0.5 line and the line where null energy is violated to all redshifts and where it's violated to no redshifts at the top here. And you can see that these DESI contours all lie with almost all of the probability below this 0.5 line here. That means that the predictions for all the BAO data at redshift of 0.5 and less are actually going in the wrong direction for models that would satisfy the null energy condition. So the constraints that appear here are strongly dependent upon allowing null energy condition violations, and therefore they may not be very physical. If you enforce the null energy condition as shown on the right here, then your contours look quite different. So now, if you take the max of these values here, this just forces the fact that WA can never be less than -1. This entire left axis then becomes lambda CDM model, and it looks, at least with Pantheon Plus, as though you're perfectly consistent within 2 sigma. And these plots here, these contours are quite strongly away from 0, of course, including the supernova data. So it's really the supernova data that are driving you into this region, the parameter space that's not consistent with the null energy condition. Forgetting about the supernova data for the moment, how bad is actually just a lambda CDM model? So this shows the plot from the DESI team in lambda CDM. of omega m versus h naught. So you can see that the CMB is off to the left here, but has this very tight degeneracy between h naught and omega m required to get the acoustic scale to be the observed value. And then the DESI constraint using BN is on the right of that. But they overlap quite reasonably here. So as long as the CMB prediction was on the right-hand side of this contour, so lower omega m and slightly higher h naught than the mean, then this looks as though this is going to be a perfectly consistent model here in this overlapping region. And fluctuations of the parameters in that direction are actually not too surprising. We know things like the sort of slight A lens tension are slightly pulling things in the direction of lower h naught and higher omega m in the Planck data. So I don't think anyone will be surprised if there's a 1 sigma statistical fluctuation in one direction. So maybe this is actually 1.5 to 2 sigma, but it's certainly not super significant. So if you plot the DESI data compared to the DESI plus Planck best fit lambda CDM model, so the point of intersection on the left here, so now the central point here is this joint fit to DESI plus lambda CDM, and you plot the DESI data. By eye, to me, this looks like a perfectly decent fit. A couple of these points are a little bit low, but bearing in mind that these are 1 sigma contours in marginalized direction, so the 2D contours are actually somewhat outside these crosses. They're not very discrepant with the lambda CDM value in the middle. Quite a lot of the points are perfectly consistent with it. So by eye, this looks like a perfectly good fit to lambda CDM, taking just the acoustic scale data, as long as you're prepared to accept that the parameters from Planck have shifted by 1.5 sigma or something in a particular direction along the degeneracy direction. So the conclusions are that the null energy condition strongly constrains what you can do with BA observable predictions in dark energy models in non-interacting FRW framework. There is a slight tension with some of the points between DESI DR2 and CMB in lambda CDM, but almost entirely in directions that are inconsistent with a null energy condition. If you actually just accept some slight shift in the parameters to do the joint best fit between them, lambda CDM doesn't look too bad. Shifts the Planck omega m down, h naught up by a bit. The thing that's really driving the pulls away from lambda CDM is the supernovae. It's not the acoustic scale data. If you do allow null energy violation and put the W0 WA model, for example, you can then get a better fit to the supernovae because it fits the shape of the supernovae at low redshift somewhat better, and it looks slightly significant. But given that W0 and WA is a totally unmotivated model, you are violating the null energy condition, and you do not get a higher value of the Hubble parameter. It seems unmotivated at this point to introduce these extra unphysical parameters when you're not also simultaneously solving the remaining Hubble tension. You'd have to have some other extra physics to solve that, or unless it gets resolved itself by some other method. So thanks for listening.